What's up, guys? Mrs. Lynch here. Yeah, I am not there today, but I did record the entire lesson for you. You better behave. I am on an avid field trip to Texas A&M. I will be back tomorrow. My 6th period and 8th period, I think it's a B day. I will see you tomorrow. But we are, 6th period, we are going to be in a different classroom. It is written on the board, I believe it's A212, if I remember correctly. This is because of the freshmen taking the English 1-star test. So we will have class in there tomorrow. 7th period, I will see you again on Wednesday. There is no testing that day, and we will be in our classroom as usual, and I will be there. So make sure you write down your notes. I tried to teach this and explain it just as I would if I would have been there in class. So enjoy the video. I hope you can understand me all right, and I will see you later. All right, here we go. So we are learning today about exponential growth and decay. Basically, these are graphs that will either shoot up very quickly or they will decrease very quickly. Things that grow exponentially are things like your bank account with interest, maybe the value of a house or a car. Actually, that would be, a car would be something that would be an example of exponential decay. The longer you have the car, the lower the value of it is, and such forth. So they are modeled with equations that look like this. Y equals A times B raised to the power of X. So exponential functions always have that variable, the X, in the actual exponent spot. All right, and so the A and the B in the equations, those represent different values. They are most likely going to be replaced with numbers. All right, the A stands for the starting value. Okay, I used the example of a car depreciating a second ago, losing its value. Well, the A in the equation is where you would plug in the actual starting value of the car. You can also think of it as the initial number or the initial value of something. Okay, B represents either the growth factor if it's growing, or potentially the decay factor. How much basically it is decreasing or increasing, and you'll be able to tell that by the value of B. Now, we can tell in an equation whether it is growing or whether it is decaying if they already give us the equation, which we're going to look at in example 1, by what the B value is. If the B value is something bigger than 1, even just like 1.1 or 1.02, anything that is bigger than 1, then that means that this is exponential growth. The value is going to get bigger. All right, anything between 0 and 1, all right, as long as the B value is greater than 0, but less than 1, all right, then we're going to have decay. Okay, decimals fall into that category, like, 0.8 or 0.23, right? Those would be examples of decay factors. All right, so looking at example 1, without graphing, determine whether each function represents exponential growth or decay Also determine the percent increase or decrease. All right, so let's look at A, this first equation. All right, so we have y equals 100 times 0.012 to the x power. Now, just to remind you, they didn't ask us about this, but this 100, that's the A value. That would be the starting value. So I don't know what this applies to, but I know the initial value is 100, right? I'm going to be able to tell if it's going to grow or decay based on the number inside the parentheses here, 0.12. That is greater than 0 and less than 1. So that means this, this function right here is an example of exponential decay. All right, now they want to know by what percentage it is decaying, it's decreasing, all right? How you figure that out is based on how much less than 1 it is. Because it's decay, we're going to subtract. We would do 1 minus 0.12, or the decay factor that they give us, which is equal to, all right, let's subtract that here. I've got my calculator. We're going to do 1 minus 0.12. Oh, clear. 1 minus 0.12, right, which is 0.88. Okay, what that tells us is that this $100 thing that we have is decaying, and it's decaying by 0.88. All right, which if we change that into a percentage, remember to change a decimal into percent, you just move the decimal 2 places to the right. That means this is going to decrease by 88%. Okay, looking at example B, all right, it has a starting value of 0.2. We can see here in the parentheses, that would be the B, in this case, it's going to be a growth factor because B is greater than 1. All right, so we're going to write that it's growth. And we want to know the percentage that it is growing. For growing, you do things the other way around. Because this is bigger, we're actually going to do 1.74 and subtract 1. It always is subtraction. It always has the number 1. All right, it just depends on whether you do 1 minus the decay factor or the growth factor minus 1 in this case, which leaves you with 0.74. As a percentage, that would be a 74% increase, or it's going to increase by 74%. Okay, moving on to example C. The initial value is 16. All right, this one, wow, that is a big growth factor. It's obviously above 1. This is going to be exponential growth. Just like we did on the last problem, if it's growth, you take the growth factor and you subtract 1 to see how much bigger it is. All right, that leaves you 2.4. All right, we can still change that into a percent. Remember, you move the decimal 2 spaces to the right, which actually makes this that there is a 240% increase. All right, whatever this is growing really fast. All right, and our last one, example D, this one looks a little different because the growth or decay factor was given as a fraction. The initial value is 32. Now, you can always turn a fraction into a decimal. You can tell here because the number is bigger on top, this is greater than 1, but just to show you by subtracting on or changing that into a decimal in the calculator, 14 over 10 is 1.4. Sorry, you couldn't see it. 1.4. So that obviously is going to be another example of growth. It's greater than 1. All right, and to see how big of percentage of growth that is, do the growth factor minus 1, which equals 0.4. All right, if that was a percentage, move the decimal 2 spots to the right, which means that this is increasing by 40%. All right, so let's look at example 2. Example 2 is actually giving us a situation now in which let me zoom out, in which we are going to write the function for the scenario given in the problem, and then we are going to find a value. All right, this is about a car. It is going to depreciate 25% each year. Write a function that models the value of the car. Right? Remember that all of our functions are going to follow this format: y equals a times b to the power of x. All right, and in this case, x is actually going to represent the number of years for us. Okay, so we are given an initial value, right? When they bought the car, or the new car sold for $18,000, right? But it's going to get less or depreciate over time. All right, so our initial value is the A, that would be the 18,000. In order to find your B value, right, remember the B value, or in this case, decay factor, would be 1 minus, and then the 25% that it decreases each year would get subtracted from that. So remember, 25% is 0.25 as a decimal. All right, which would leave us, the B value for this one is going to be 0.75. And that's kind of the reverse of what we were doing in those example 1 problems. All right, so writing out the equation, it would be y equals 18,000 times 0.75 to the power of x. Okay, now that's the function that models the value of the car. The second part of this is they want us to actually find the value of the car after 4 years, right? The x, or the exponent, is representing the time. Right? So we're actually going to plug that in there and evaluate, and to do so we can use our calculator. All right, so we've got 0.75 to the 4th power. That's the first thing you're going to plug in the calculator. Remember, in PEMDAS, parentheses and exponents comes first. So I would do 0.75, and I'm going to press the little caret key so that I can do an exponent power of 4. Let's see how much that is. All right, so that gives us that value on the screen. Okay, I am going to multiply that with, so just immediately hit the multiply button, times the 18,000, or the initial amount that was in the front. So now I'm going to type in times 18,000 and see how much we get. We're probably going to have to round. I think rounding, since this is money, we're going to round to the nearest penny, which would be 2 decimal spaces. So we're going to say the value after 4 years is going to be 5,000. Let me see what it said again. $5,695.31. $695.31. All right, and that would complete that example. Example 3, we have an abandoned house. It has a mouse population of 22. It is increasing at a rate of 5% per month. Write a function that models the population. Estimate when there will be 50 mice in the house. Okay, so here, that scenario sounds disturbing. All right, so we're starting with initial population of 22 mice. All right, so that is going to be our A value, our starting value. All right, it is actually increasing. So our B value has to be over 1. All right, so it's going to be 1 plus that extra 5%. 5% as a decimal is 0.05. And so by putting those together, 1.05 is going to be our growth factor. All right, again, we write our equation in this format, a times b to the power of x. And x is going to be representing time again, but we're going to use it as months because this is increasing each month. All right, so let's fill in the values. We have y equals 22 times 1.05 to the x power. Now, they're asking us to do something a little differently on this one. They're asking us to figure out how many months it would take for there to be about 50 mice in the house. So instead of plugging 50, 50 does not represent the months. We're actually going to solve for x, and where we're going to place our 50 is actually in the y value. We're going to say 50 is equal to 22 times 1.05 to the x power. To simplify this and kind of solve it, since this is multiplying 22 times, we can actually start to get this x by itself by dividing by 22 on both sides. All right, 50 divided by 22 leaves us with about 2.27. I'm gonna leave it, let's say 2.273 just to be safe. 2.273, this is gone, is equal to 1.05 to the x. All right, now later on we are actually gonna learn how to really solve this. You use something called logs, but for the time being, we're just going to use our calculator and our y equals function to get an estimate to solve this. So what I'm going to do is go to y equals, and I'm going to type in this 1.05 to the x that I have. 1.05 raised to the x power. All right. And then I'm going to go to the table function. What I'm looking for is a y value that is close to 2.273. All right, we're probably not going to see it exactly. All right, starting at 0 months, you can see we have 1. All right, we're going down, we're getting closer to 2, 12, 13, okay, at 15 months, we get 2.07. At 16 months, we get 2.18. That's a little less. At 17 months, we get 2.292, which is actually a little bit more. All right, so here's where we're taking this as an estimate. It's going to reach that population of 50 mice somewhere between 16 and 17 months because 2.273 is in between those two values right there. All right, so that's actually how we're going to answer it. It's going to hit there. We're going to estimate it's going to be between the 16th and 17th month mark. And that's it. So once you just kind of get it set up, you just use your calculator and the table to get an estimate. Later on, I will go back to this problem, probably, I think it's in lesson 2 or lesson 3, and show you how to actually solve it without having to do that. All right, so moving on to example 4. Write an exponential function for y equals a times b to the x for a graph that includes these 2 points. All right, so what we're going to do here is we're going to actually use our first point, which has obviously the first one is our x value and the second coordinate is our y value. There we go. And we're going to use that to solve for a. So we know that our exponential equations are set up as y equals a times b to the x. Well, they've given us a x value and a y value. And so what we're going to do is plug them into this. So y is 2, so it's going to be 2 equals a times b, and x is 0, which means that that 0 is going to get plugged into the x spot. Well, something that you may not remember, right, is actually that whenever you have anything, any number, all right, to the 0 power, let me show you what it's equal to. So there's 2 to the 0 power. It's 1. If I do 5 to the 0 power, it's 1. If I do negative 3.6 to the 0 power, well, because I typed in the negative, it said it's negative 1, but I should have put it in parentheses, basically. Anyways, it's 1, all right? When you raise something to the 0 power, it becomes 1. So what this actually turns into is 2 is equal to a times 1, and a times 1 is just a. So 2 is the value of a, or a is equal to 2, all right? And so that helps us figure out our b value later. Now that we know what a is, we're gonna use our second set of coordinates and what we've learned about the value of a so that we can solve for b now, all right? Using our same equation, this time we're gonna plug in our new y value. Our new y value is 6, all right? So we have 6 is equal to, okay, then we're going to plug in our a value. Our a value is 2 times b to the x, and our x value is 1. All right. Well, b to the first power, like we have here, is just b. So this is 6 is equal to 2b. And now we can solve for b by dividing by 2 on both sides. And so you get b is equal to 3. All right, now that we know our a value and our b value, we can fill out the final equation. All right, this time we don't have to plug in a y or an x because we know our a and b values. Our final equation, our exponential function, will be y equals a times b, so 2 times 3 to the x power. All right, now let's do another one like that. Same setup. This one's going to be just a bit more complicated though. All right, we are again going to solve for a first. All right, here is our x value, here's our y value. Okay, we've got y equals, so y equals a times b to the x. Let's plug in the values that we do know. 4 is equal to, we do not know what a is yet, we don't know what b is yet. Our x value is going to be squared. All right, now in this case, it's not as easy because b squared, we don't know what number that's actually going to become, but we're still gonna solve for a just like we did. In order to solve for a, or to get a by itself, we're gonna have to divide by b squared so that it cancels on that side. Whatever you do to one side, you have to do to the other. All right, and so what we're left with is a is equal to 4 over b squared. We obviously can't simplify that. Keep that in mind. We're going to use that and plug that into our second equation. All right, now using x and y from our second point. All right, so we're going to start with our y equals a times b to the x again. And this time we're going to plug in our y, 16, equals, and we're going to plug this in for what a equals. So we're going to plug in 4 over b squared. All right, and then we have b times b to the third power. X is 3, so we plug in 3. Okay, so what we know about exponents is right now we basically have a 4b to the third divided by a b squared. Remember, when you divide with exponents, you basically subtract. So 3 minus 2 would leave us with b to the first. All right, so simplifying this is going to become 16 is equal to 4b to the first power, or just b. Okay, then we'll be able to divide by 4 on both sides so that we have b all by itself. All right, and so b is equal to 4. 16 divided by 4 is 4. All right, and so we have b. Now, we didn't actually get a. Remember before, we didn't have a solid number answer for A. But now that we know what B is, we can go back, take this number, and plug it back in over here. All right, so I left a little bit of space for that. All right, A equals 4 divided by, and B is 4. That's going to be B squared, 4 over 16. All right, that is a fraction. If you divide it, it will be a decimal. What I would do is just reduce it. 4 over 16 reduces down to 1/4, and I would leave it like that. All right, we have our A, we have our B. We're going to write out our final equation like we did over here, leaving our Y and our X blank this time. All right, our equation will be Y equals, your A goes first, A is 1/4, times B, which was 4 to the X power. All right, luckily the example 5 is a lot easier. All we are doing is finding the annual rate of change. All right, find the growth or decay factor. So this is saying there's an increase in 35%. They just want us to find the growth factor then. Obviously this is growth. To find the growth factor, remember your percentage needs to be a decimal, and your growth factor is going to be greater than 1. So we're going to do 1 plus 35% is 0.35, which would give you a growth factor of 1.35. All right, that's all you have to do for that kind of problem. For B, this is obviously a decrease. All right, so it's going to be less than 1, meaning we're going to have to do 1 minus so that we get a decimal less than 1. Now, 47% is the same thing as 0.47, so that's what we should subtract. I'm going to use my calculator to subtract 1 minus 0.47 would leave us with a decay factor of 0.53. Final answer, moving on. All right, so exponential functions are used to represent many different real-life situations. Here are a few, and you will see problems like this on the homework and later on the quiz and test. The first real-world example type we're going to look at is the Richter scale. The energy released by an earthquake can be represented by the equation E times 30 to the power of X, where X is the magnitude of the earthquake on the Richter scale. So now something to note is the letter E represents the amount of energy that was present in the earth originally. It's actually not important for the application that we're going to use. It's going to end up canceling out. So if you look at example 1, they said in 1995, an earthquake in Mexico registered an 8.0 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook Washington state. Compare the amounts of energy released in the two earthquakes. So when we compare, what we're going to do is set them as a fraction. I'm going to put Mexico because it was first on top of the Washington one. Now remember, the equation is E times 30 to the power of x, and the x represents the magnitude. So the Mexico one was an 8.0, or basically to the power of 8. And then we're going to put that on top of the equation for the Washington one, which was E times 30. And on the Richter scale, it was a 6.8. So 6.8 is the exponent for that one. Now, like I said, the e's, because it would be the same number or at least negligible, they are going to cancel out since there is one on top and bottom. We cannot do that with the 30s because these have exponents attached to them, therefore making them different numbers. But what we can do is simplify this using our exponent rules since they have the same base. So remember, since we're dividing, you can subtract the exponents. So basically what this would become is 30, and then if you do 8 minus 6.8, or subtract the magnitudes, 8 minus 6.8, that would be 1.2. So this becomes 30 to the 1.2 power. Now, let's actually see how much that is. 30 raised to the power of 1.2 gives us 59.23, rounding it off. Okay, basically that number tells us how much stronger, or how many times stronger, the top earthquake, the Mexico earthquake, was compared to the Washington one. All right, so it means the Mexico earthquake was 59.23 times stronger. All right, and so that's what you're going to do on problems that use the Richter scale, earthquake problems. All right, another real-world example that uses exponential growth or decay functions is half-life. And if you've taken chemistry or you're going to take chemistry, this is something that you will talk about. It is the method of figuring out how old certain substances are. When we know how quickly the substance decays, we use that information to find out how long it's been sitting around, right? And the equation that you use for half-life is y equals a times 1/2, hence the term half-life, to the power of t on top of k. So that's actually a fraction as the exponent. All right, just like usual, a represents the starting value or the initial value, or the initial amount, in this case, of some substance. T is going to represent time, and K is going to represent the half-life value that they're going to give you in the problem. Okay, so let's look at example 2. Technetium 99M has a half-life of 6 hours. Find the amount that remains from a 50 milligram supply after 25 hours. So A is our initial amount. So that is starting with 50 milligrams. A equals 50. All right, T in our problem, T for time, is going to represent, they want us to say how much there's going to be after 25 hours. All right, and then K is the half-life, and they told us that the half-life is 6 hours long. All right, so we're going to fill in those values into our equation. Y equals A times 1/2 to the T over K. All right, for us, A was 50 times 1/2. That's already filled in. T over K, so T was 25 divided by K was the half-life of 6. All right, when I solve that, I'm going to go ahead and turn that into a decimal real quick. So y equals 50 times 1/2. If I do 25 divided by 6, oops, I don't really need that here. Let's do that again. 25 divided by 6, that's like 4.167. All right, so that's to the power of 4.167. All right, I'll evaluate this part first. Remember, exponents, parentheses, exponents comes first in PEMDAS. All right, so I'm going to do 1/2, which is the same thing as 0.5 raised to the power of 4.167, which would give us about 0.055, all right, times 50. Okay, all right, so y equals 50 times, that gave us 0.055, let's say about that, 0.0557, and then if you multiply that times the 50, which I did kind of already on my calculator in this step here, times 50, you get 2.78. Let's say 2.78. All right, that means after 25 years from that original 50 milligrams that we started with, there would only be 2.78 milligrams left. All right, and so that's how half-lives work. Here's another one with arsenic. Let's change this out. Example B, arsenic is used to locate brain tumors. It has a half-life of 17.5 days, right? That's your K value. Remember, K value is the half-life, 17.5 days. Write an exponential decay function for a 90 milligram sample. All right, so that's how much they're starting with, 90 milligrams. And use it to find how much is remaining after 6 days. So the time we want to look at specifically is the time for 6 days. Now, all the functions are written in this format, y equals a times 1/2 to the power of t divided by k. We do already know the a value. We know the k value. And we also know the t value that they want us to evaluate. So y equals, let's fill those in, 90 times 1/2. T is 6 divided by the half-life, which is 17.5. I'm going to do that part on my calculator first. The t divided by k, 6 divided by 17.5 is 0.34, let's say 0.343. All right, I'm going to do the 1/2 to the 0.343 power. Remember, 1/2 is 0.5. I'm just going to type it in that way so it's easier. Okay, we're going to round that, let's say 0.788. Okay, so now we have y equals 90 times 0.788, and I'm going to multiply that 0.788 times 90 to get my final answer, which is going to give us y equals 70.96 if we round up milligrams remaining of arsenic. All right, final answer And that's how you do half-life. Now, another example, real life example, is compounded interest. When you put money in an investment account or even just a bank, it collects interest. This means that the bank will give you a small amount of money just for letting your money sit in their bank. Interest is compounded or calculated a certain number of times per year. So for this is a little bit more complicated of an equation, all right? The equation for compounded interest is y equals A, which is still your initial amount, times 1 plus r divided by n, that's all in parentheses, raised to an exponent that is n times t. All right, now I'm going to tell you what all those variables mean. A is your initial amount as per usual. This time it's going to be an initial amount of money that you start with in the bank. N, the letter N, is going to stand for the number of times that it is compounded. Okay. R, the variable R, is going to equal the interest rate that they give you. All right, and then T is going to represent time. Okay, so example 3. You invest $100 at an annual interest rate of 4% that is compounded quarterly. How much money will you have in the account after 25 years? All right, so the different values we need to know. The initial amount, all right, we're investing $100. That's what we're going to put into the bank, all right? Now, in the number of times it is compounded, that comes from, they tell us that it's compounded quarterly. Quarterly means that it's basically happens 4 times a year. That's each quarter of the year. So our N is going to be 4. All right. Our R is our interest rate. That's 4%. All right. 4% written as a decimal is 0.04. We are going to change it into a decimal. And then T, the amount of time, is we want to know how much money will be there after 25 years. So time is going to be 25 years, all right? And so we're going to fill in our equation that I told you that we work with those different numbers. So y is equal to, A was 100 times 1 plus r divided by n. So 0.04, n is 4, all right? Raised to the power of n times t, so 4 times 25 is going to go up there as the exponent. All right, we're going to simplify this. We can obviously, 4 times 25 is going to be 100, but I also want to simplify this that's in the parentheses as well. So I'm going to do 0.04 divided by 4, which is 0.01, plus the 1 that I had. All right, so that's going to give us 1.01 to go inside the parentheses. Y equals 100 times 1.01 raised to, and 4 times 25 is 100. All right, and then we can evaluate that. I'm going to do 1.01 to the 100th power to see what we get, so that I know what we're going to multiply with. So 1.01 to the 100th power is 2.705 times 2.075. Multiply that times 100, and we'll have $270.48. So that's not a whole lot for 25 years, but that's because it's a very low 4% interest rate. But I mean, your money did over double, so you know, it's better than not investing it. All right, so the last type we're going to look at is continuously compounded interest. So this is what it sounds like. There is not a certain number of times that the interest is calculated per year. It's done continuously or all the time. And so there's a different formula that we use for this kind of situation. It is, and the equation is A is equal to P times E to the RT. So we're going to talk about E later on, but E is a number in itself. It's kind of like pi. It is a number that never ends. And we do have the E button on our calculator. All right, you can see it's actually in blue. I'm gonna zoom in a little bit. Oops, wrong way. It's actually in blue right here underneath pi. That's E. I wanna show you. I'm gonna press that and put it on the screen so it can show you like about what it's equal to. So there's E, and I'm going to press enter so you can see. So E is about 2.7, and it does keep going on forever though, so it cuts it off obviously on the calculator, but we're gonna be able to enter it just as E in our calculator. And you can also do E to an exponent. That is right here. You see this button that says LN. Right, it's in blue just above that E to the X. So we can give it a different exponent if we need to. All right, so anyways, that's what E is. Now these other values, what they are, P represents the initial amount. This is the only time we haven't used A for the initial amount. I don't know why they change it to P in this equation, but they do. R represents your interest rate, just like in the last problem, and T is equal to time. All right, and then I think A, the big A, is just representing how much is in the account or the amount at the end. All right, so we're going to invest $1,050 at an annual rate of 5.5% compounded continuously. How much money will you have in the account after 10 years? All right, so A is equal to P times E to the RT. All right, P is the starting amount. We're gonna have $1,050 that we plug in there. The interest rate is 5.5%, but we need to write it as a decimal. All right, moving the decimal place back, that would be 0.055. And then time is going to be 10 years because that's what they ask about in the equation. So we're going to plug those in. A is equal to 1050 times E to the R times T. So 0.055 times 10 is all in the exponent. If you multiply those, 0.055 times 10, you actually get 0.55, the decimal, there's not the 0.0 anymore. All right, and then we're gonna raise E. We're gonna do the exponent, E to the 0.55 power. So like I said, you can go to that LN button, but you have to press second and then the LN button. You can see my E on the screen and the space to put the exponent up high. I type in my 0.55, enter. So that's about 1.733. Okay, so now I have A equals 1050 times 1.733. If we, wow, that looks funky. Oh, whatever. All right, so now we multiply them. And after 10 years, you should have $1,819.90. We need to round up 92 cents in your account. All right, last one. A student wants to save $8,000 for college in 5 years. How much should an account that earns 5.2 annual interest, or how much should be put into an account that earns 5.2 annual interest compounded continuously? So this time they're asking us how much should be put into the account. So they're not telling us the starting amount. So if P is the initial amount, we're actually going to figure that out. What they did tell us, the 8,000, that's how much she wants to be there at the end. And so we actually know the A for this one. Now, they did give us the interest rate is 5.2. Right? Remember, interest rate is represented by R, and written as a decimal will be 0.052. And then it's only going to be there for 5 years. So T is 5. All right, so our equation, all right, for compounded continuously interest looks like this. We know that A is 8,000. We don't know the P, so just leave that alone. E is the constant, which we know is about 2.7, kind of like pi. It doesn't end. All right, R is 0.052, and we're going to multiply that times time, which is 5. So let's multiply those first. 0.052 times 5 is 0.26. All right, so 8,000 equals P times E to the 0.26 power. Let's do E to the 0.26 power. So I do my second, my LN button, E to the 0.26, press enter. That is about 1.297, let's say 1.297. So 8,000 equals P times 1.297. And since we're solving for P, we're solving this backwards and this is multiplying, we need to divide to get P by itself. So divide by 1.297 on each side so that it cancels. All right, and P, the amount we need to invest, let's solve that, divided by 1.297, enter, $6,168 and about 8 cents. $6,168.08 is how much she needs to put in the account today so that in 5 years she'll have $8,000 there. All right, that's gonna be it. That was really long. I apologize for the length, but that was just a really long lesson with a lot to cover. The sub is going to pass out your homework, so you can get started on that. I'll see you in class next time.